Welcome back, everybody. We have skipped past the examples from the first part here, and we've actually jumped down to the bottom of the third page, I believe, that has the squeeze theorem. So this is a very interesting theorem that comes up with some very particular cases that we're going to look at. So it's not an analytical method per se, like factoring or finding common denominators or direct substitution. It's really analyzing what the graph is doing as it approaches the value we're interested in, and our ability to create a boundary or a sandwich or a way to squeeze our function in between two other functions. So for the example we're going to look at, we've got the graph on the right here, and we've got the function itself. And so the function is an interesting function. It's x squared times sine of 1 over x, and again that's inside of the sine, so that's the angle argument. So we've got this x squared function, which is a quadratic, and we can see in the graph here they've actually graphed x squared and negative x squared, so you might be wondering, why are they doing that? And sine of 1 over x. So before we get into that, I actually want to look at it with just the function itself. So this is x squared sine 1 over x. We've got this kind of interesting wavy behavior on the outside. X squared sine 1 over x is an odd function because sine is an odd function. X squared is an even function, but that sine 1 over x will give us the symmetry about the line y equals x. About the line symmetry about y equals x. But, you know, if we look at the graph here, it's kind of obvious what our limit's going to be, right? But that's because we have the benefit of the graph in front of us. And so the question is, what if I didn't have this graph in front of us? What would we do? And that's where the squeeze theorem is going to come in. And in particular for the squeeze theorem, we'll look at the definition first, and then we'll discuss how to use it. So for the squeeze theorem, we do need three functions with some particular properties. So f and h are bounded above and below functions. So f is going to be below g, and h is going to be above g or equal to it. So we can have equality as well. And so g is really the one that we're interested in. And what the theorem says that is if the limit of the two above and below functions is the same value, whatever that value is, then the function between, the function that is sandwiched between or squeezed between those two functions, is that same value. It has to be equal to L. And so this seems pretty obvious that this should be true. So let's see if we can apply this theorem to this example without reference to our graph, right? So we want to show that the limit as x approaches 0 of x squared sine 1 over x is 0. Now we could argue that x squared and sine 1 over x have particular behaviors. And that's really what we're going to use here. So what we're going to use here is what we know about both of these functions. And so we'll start with, when looking at these two functions, are either of these two functions bounded, right? So if I have x squared, or if I have sine 1 over x, which is going to be that function that we looked at before, where it's, looks like this, and then it kind of goes out, and then it kind of goes out. So quadratic, clearly approaching infinity, not bounded above. It's bounded below, but not bounded above. So it's got almost a boundary point condition met, but it is not bounded above. Sine, however, is bounded, right? So we know that it lies somewhere between negative 1 and 1, no matter what sine 1 over x looks like. So we're going to start with the argument that we know. Let's do a smaller font here. We know that sine 1 over x is between negative 1 and 1. Thus, if we multiply our inequality through by x squared, we know that negative x squared and x squared is going to be the boundaries both below and above. Right? So x squared is always above our function, and negative x squared is always below. Okay. Now we would have to be slightly careful if it was like just x, right? Because we could get sign changes and things like that, but x squared is also always positive, so we don't have to worry about this sign changing at all. So we do have to be slightly careful. All right, so, and the limit as x approaches 0, negative x squared is the same as the limit as x approaches 0 of x squared. Boom, our condition is met. So that equals 0. Thus, or I've used thus, so let's add a different word here. Hence, by the squeeze theorem or the sandwich theorem, whatever you want to call it, the limit as x approaches 0 of x squared sine 1 over x is also equal to 0. QED. So there's really two main ideas. We need an inequality boundary above and below for our functions, and we need the limits to be the same. Those two conditions are met, then it follows by the squeeze theorem that we'll have the same value of the limit below. Okay. So going back here, oops. So again, if we have the graph, it's very easy to see. If we don't have the graph, then we would want to refer to the more analytical approach where we're writing out an actual proof. And just note on Desmos, perfect boundary points everywhere. But do notice that as we get further to the left or to the right, the graph is always above and below, but it is much further away. So there's this small little section where the graphs are almost the same at a bunch of points. All right, and so that is the squeeze theorem. You're going to see it from time to time a little bit here. You're going to see it in your homework as well. So if you have questions, let me know.